Okay, so thanks first of all for the invitation. It's very nice to be here. So I was really pleased to hear that I can here present something which maybe many of people from our community, from quantum information, have already seen, also to a slightly broader audience of people who are also dealing with quantum mechanics on a much larger scale. So actually maybe the main message here, and you may also wonder how this fits into this whole workshop, is that before we even go to very large scales, we already have in certain situations, as we will see, problems understanding what quantum theory tells us on relatively moderate scales. And by moderate scales, I mean scales where we talk about systems which are sufficiently large that they can contain what we would call maybe an observer or an agent. So I'm talking about this kind of, let's say, big scale where we have, of course, not tested quantum theory, but in all what I'm going to tell you, I'm going to assume that there is no boundary on the size or complexity of the systems to which quantum mechanics applies. Of course, we don't know that, but you can also regard this whole thing as a test, as a theoretical test of what happens if you apply quantum mechanics to large systems. And one conclusion could be that it actually doesn't work, but I leave it up to you to make your conclusions, and I will just essentially describe a thought experiment. To start, I will describe a very basic and well-known thought experiment, the Wigner's friend thought experiment that has been mentioned several times already, but because I think not everyone is very familiar with it, I will spend the first 5 minutes on that, and then I will, after these 5 or 10 minutes, wake up all the others who already knew it and fell asleep maybe during that time, and then you can continue with the, let's say, more interesting part. So the way I'm going to draw it is I will essentially think of time as running from left to right. So this is just a way to represent things. I will just draw pictures essentially, but in these pictures you should kind of understand that what I draw left happens before what I draw right. And I will here to actually be explicit when I will talk about time. So times will be important. So I will talk about states of systems at different times, and we cannot neglect the times. I will here say we start somehow at a certain point, which I may call midnight, and then we continue and say this is 10 minutes after midnight, something will happen here, and then we'll have something else here.
Do you expect us to be awake at all these times?
Yes. So let's see. So I will between each of these intervals, someone is supposed to do something, and so you see, they have enough time to do. You can also interpret that as seconds, if you like. So it's maybe 10 seconds after midnight. Anyway, so I will start with the standard Wigner's friend experiment, where one imagines that one has a lab which is isolated. And I will call this lab L. And in this lab there is a person, Wigner's friend, and I will just indicate that here because we will have several agents, and I will call these persons agents, and you will see what that means. I mean, at the moment there's no other, or maybe I should say that now, because there's always this question, what do you mean by an agent? Actually, I don't know really, but the only thing I require is that an agent is someone who could do physics. So actually at the end we are going to describe systems using quantum mechanics, and the systems contain agents who themselves apply quantum mechanics. So it's in some way a recursive use of the theory. We describe someone who uses quantum mechanics using quantum mechanics. So that's maybe kind of the big theme here. And therefore we have to talk about different agents, and I will give names to them. And this girl here in the box I call F for Wigner's friend. And the only task she has is, so I said the lab is isolated. This is not completely true. I will assume that one qubit can enter the lab, or if you want you can talk about the spin. I will maybe talk about the spin in the future. There's a spin particle entering the lab, and the task she has is to measure this spin particle in a basis which I could call, let's say, the up-down basis. So this is just up and down, and there will be a measurement outcome which I will call Z. And this Z will indicate what is the vertical spin, measured spin direction, which is -1/2 or +1/2. This is just a labeling. It will not be important. But this is just two possible outcomes. Okay. So this is actually already almost all that happens in Wigner's salt experiment. But of course, the interesting part is not this measurement, but the analysis he does. So Wigner's idea was to analyze this experiment from two perspectives, namely from the perspective of this person who is inside the lab and from the perspective of someone who may stand here. I will draw this guy later. He will also do something, Wigner. He will also analyze this experiment. And now, let me just start writing down what these people would actually write down if they did an analysis. So, what could, I mean, for F, it's probably obvious what she would do. She would, for example, after having seen the value set, she would say now, let's assume, by the way, that this measurement is non-destructive. So the spin still exists. So what F would say is the following. She would say that if, for example, the measurement outcome was +1/2, then she knows essentially that the spin direction is down. I will just indicate it like that. So then the spin S system will be in the up state, and correspondingly, if this is -1/2, then this is down. So that's, of course, what you know. I mean, that's what we mean by a measurement. There's not even an interpretation. That's what we mean by a non-destructive measurement. What Wigner could say, he's the person outside. He would just, I mean, for him it depends on what the initial state was. And let's start with something simple. So let's assume that the initial state, which I may call phi s, so this is the state at time 10, before the measurement starts. So let's say, he would say that if phi s is equal to spin up at, I will always write these times because this is going to be important later, then the outcome set, then, and now he doesn't see the outcome set. So from Wigner's perspective, this is just a huge quantum system. And this huge quantum system, he will just treat using quantum mechanics and therefore assign a state to it. And let's suppose that Wigner now says, okay, this big quantum system at this time here, at time 20, has a certain state, which I will indicate with a big psi L. So L is for the lab. So he would just say psi L is now equal to, and now he assigns this is a famous big entangled, or not entangled, but a multi-party set. He would say, okay, the spin in the lab is probably up, if it was initially up, because it's a non-destructive measurement. Then he could also assign to states to the things in the lab. So you would say maybe in this lab there's a device and the device shows +1/2. So this is a state which is just defined as the state of the device when it shows the outcome +1/2. And there is even a person in the lab, and this person knows that the outcome is +1/2 because she has probably read the outcome. And so this is a huge, a state of a huge system. But I'm not, for what I'm going to do, it will not be relevant at all what the structure of this state is. I will just denote this state by something I call +1/2 of L. This is just defined to be the state of the lab if the input here to the lab, if the initial spin direction was up. And you can think of it however you like, but this is usually, if you read Wigner's paper, for example, this is the state he would assign to that. And of course, I could do the same thing for down, and so I just have to copy. This is a bit boring, but then psi L would of course be that the spin is down, the measurement device shows -1/2, and this is, the friend also knows it's -1/2. And this state, of course, I can use the same notation and say this is the -1/2 state of L. So, okay, so far there was also nothing particularly interesting. Now the situation that Wigner was worried about was the one where the input is now not up or down, but where the input phi S is, for example, spin right. And let's just make the convention that spin right, this is just a convention, means up plus down. So what is then the state of the lab? And now, for the moment, I haven't even used that the lab is isolated. But now if the lab is isolated, which I will assume in the following, then, of course, the evolution according to our current understanding of quantum theory, without any additional, let's say, objective or physical collapse mechanisms, I'm not talking about collapse models here, will just evolve, so that it will evolve you linearly, and by linearity I can now just use what I wrote here. So the state will be in this superposition of the lab being in the situation as if the spin was plus 1/2, and in the situation as if the input spin was minus 1/2. So that's the very well-known thing. So there's nothing that should surprise you, because that's what you read when you read about measurement problems and so on. Now it was the idea of, I think, of several people in the past, but it's maybe very explicitly, for example, described in a paper by Deutsch, that we could, in principle, if we had good enough technology, even verify that. So we could imagine, and that's why I actually drew this guy, Wigner here, that he and the reason why it's much later, it's maybe at the moment not clear, but let's suppose nothing happens here between time 20 and 30, but here at time 30, he applies a measurement to this thing. And he wants to verify whether the system is indeed in the state that I claimed here it should be. So now, for later purposes, I will denote the vectors with respect to which he will measure by OK and fail. So what are they? I haven't defined them yet. So this would be the vector that I call fail. And then, so that's just a vector of the lab. It's a superposition of the lab being 1/2 and minus 1/2. And I could also define a corresponding vector OK of the lab, which is the same thing with a minus sign in between. So that's just a definition. And now, if he does this measurement, there is an outcome which I call W. Okay, and now according to what I said, of course, if this measurement is carried out, and we started from this situation, so I will write this here. So what W could say is that if phi s was the state spin right at time 10, then the outcome W will be equal to something at time, let's say, this is before the next so the measurements always, let's say, take at most 9 minutes so that it's ready at the next time. So let's say at time 39 is determined. So what is it? So it's probably obvious what this measurement outcome is. So it will be fail, because fail was just defined to be that vector. I hope that's clear so far. If not, please complain, because that finishes now the kind of review of what Wigner would have said about that. So Wigner just analyzed or wrote this down and said, in principle, if quantum mechanics was true, this final state of the system would be that state fail, which is in some way, if you look at these individual components, a huge entangled state. It's kind of a Schrödinger cat state, if you like. Some people use that terminology. So I hope up to this point, everything is well known. So it's probably the time for those who already knew all that to come back. And because I will now continue with, first of all, a few remarks about this, which are important to understand what I'm going to do, as a motivation of what I'm going to do, and also then the extension of that. So first of all, one could say this is already problematic, because we have now two agents who assign kind of different states to the system. Because clearly, even if we are in this situation where we have the spin right, the friend in the lab will either assign the state up or down to the spin, because he sees the outcome set. Whereas Wigner, who is outside, will assign this complicated state fail that I wrote here to to the entire system. And one could now say this is a contradiction, two agents assign different states to a system. But actually, most interpretations of quantum mechanics that we have today, and there are many, I mean, ranging from extensions like Bohmian mechanics to cubism, they all are kind of built around that problem in such a way that they solve it in a certain way. So most... Yes?
What is it contradicting?
Yes, so that's actually the point. So what I want to say is that most current interpretations would say there is no contradiction. So my point is really, of course, Wigner thought it's a contradiction, concluded from that there must be a collapse caused by the conscious perception that this friend has. But this was in the past. And modern interpretations would all say there's actually no problem, we just have to interpret quantum mechanics right. Just to give you an example, so one thing is Bohmian mechanics, and in Bohmian mechanics one would just say, okay, actually there is really an outcome, so this particle will, for example, there's a measurement device and a pointer, and this pointer will actually show +1/2 or -1/2. This is just a hidden variable, or we call it